Hi, I'm Guy. So today I'd like to talk about work on improving the machine outliner. So the machine outliner pass is perhaps one of the most famous paths in the backend. So the goal is to reduce code size, and it does so by replacing repeated sequences of instructions with calls to a shared function. Right. So in this example here, we have a sequence that has a repeat sequence that occurred twice. So what the parser will do is to create a separate function, outline function 1, and replace the sequences with call to the function. So for this example here, we can save around 2 instructions just by doing so. So the recent effort has been focusing on to try to make machine outliner global. Because the traditional compiler flow, we work on one file at a time, so one compilation at a time. So without LTO, we can actually only get a very small amount of benefit. So I'd like to illustrate the point with the example here. So let's say I have 2 files, A.O and B.O, and the goal is to outline the sequence A since it appeared twice. But without LTO, when we are compiling A.O, we won't be able to see the content of B. So we won't be able to see that sequence A is actually beneficial for outlining. So as a result, we missed opportunity for outlining sequence A. So the other approach is based on full LTO, where the idea is basically we merge all the files into a single merged compilation unit, and we run our passes on this single compilation unit. As shown here, now the pass can see that sequence A actually appeared twice. So to outline it, and this will lead to a better optimization result. But the problem here is compilation time. Since in full LTO, we have to optimize the merged module always using one single thread, and this will result in a very long compilation time. So a more promising approach is based on single LTO, where the idea is basically we try to generate a summary efficiently that capture what we are trying to optimize for. So in this context, our summary will be something like this. So we summarize all the repeated sequences in my CUs. For example, here, my summary will say sequence A appeared twice globally. And then when we compile A and B in parallel, we look at the summary and decide if we want to outline A. So for example, when we are compiling A.O, we see that sequence A appeared twice globally. So we will instead outline it, and then we rely on the linker to duplicate the 2 outline sequences. And this is how we save code size with single LTO. So I'd like to dive more into detail of how some of the recent works to use single LTO for machine outliner. So this work done a few years back is essentially use a 2-round code generation approach for single LTO. So the first round is only used for generating the summary. So it's actually pretty straightforward. So we run the flow all the way until the machine outliner in the code gen phase. And right there, for each compilation unit, we dump out a local summary of the sequences within my current compilation unit. And then we are doing single LTO, we will merge those local summary into a global one. So that the global summary will contain information of all the beneficial sequences that we wish to outline. And then after this summary generation, we immediately kick off another round, the second round of code generation, which will query the summary that we just generated. And by doing this, we're able to do the global optimization within single LTO. However, as you can see, since we have to repeat the code gen in a sense, so that this will still increase the compilation time by around 50%. So naturally, in our build pipeline, we actually want to further improve the compilation time. And we have this following observation. So in our production pipeline, we find that our apps actually evolve quite slowly in the sense that we won't be changing most of the source code within a short period of time. So that means the summaries actually stayed pretty much the same across consecutive builds within, let's say, 1 day. So we really don't need to generate a new summary per build. We can reuse the summary from, let's say, a recent build. So this is basically our idea. So we want to decouple the summary generation versus the summary consumption. This is in a way similar to PGO, but it's actually even simpler in the sense that the profiling is done during compilation rather than actually running the program. So we basically define two kinds of builds. In the profile build, we simply run the normal compilation all the way to machine outliner, and we generate a summary, and then we stop right there. And during the production builds that we run many, many times in a day, we directly use the summary that we just generated, let's say on a daily basis. And now since the production run only needs to read summary, this can significantly speed up our release build time. And here's a high-level design of the flow. So on the left side, like I described, in the profile build, we generate a local summary, and we have offline step to merge them into a global summary. And during the production build, the only overhead is to read this global summary. And all the other steps are basically the same. We run everything in parallel. So here are some of the implementation details. So in our summary, each entry is a pair where the first element is a hash representing the sequence. This hash is stable across compilation unit, and we utilize the stable hash functionality within the LLVM backend. The second element is the frequency of that particular sequence. So the higher the frequency, the more likely it is beneficial to outline from. And as you might have noticed, reading the summary actually is the bottleneck. So we really want to reduce the overhead of reading it. So we have two techniques here. So the first thing is we really want to generate small summaries. And the way we do it is by adding a flag called the mean sequence frequency. So this controls the minimum occurrence of sequences in my global summary. So for example, if I set it to 4, then any sequence that appeared lasted 4 times will be discarded, and we won't have it in the global summary. The other thing is to, in order to enable fast lookup, we actually pre-sort those hashes in the global summary. So during production build, we can do binary search when we do the lookup. So we choose not to generate a in-memory map-like structure for the summary because simply converting the file into a map is already too costly. And lastly, in the production build, the outliner in order for the outliner to consider the global effect, we change the cost function slightly. So here the only change is when we count the occurrence of the summary. So we have the global occurrence count right here. And with this, we will be able to consider the global effect of outlining while we are only compiling our local file. So here we did a quick experiment on a demo Swift app. This is relatively small with only around the 10 megabytes binary size. And we vary the mean sequence frequency parameter to see its effect on both the summary file size and the binary size. So on the right-hand side, we can actually see that with a mean frequency of 8, we can actually reduce the summary size by almost 10 times compared to the baseline where the mean frequency is 2. And on the left side, we see that the binary size actually can consistently reduce by around 10%, even with a mean frequency of 8. So this also shows that, at least for this program, the low frequency sequences actually do not matter that much, which is also intuitive because they don't really contribute to much of the savings that we have. In terms of compile time, since this app is really small, we can barely measure the difference in the overall build time. And in our internal larger apps with a mean frequency of 4, our compile time overhead is less than 10%. Okay, so in summary, first, since in our production environment, we care a lot about compilation time, we proposed a profiling-based technique to speed up global machine outlining by doing the summary generation offline. And in the future, we plan to apply this approach to other kinds of global optimizations, such as function merging. And that's it. Thanks.
Okay, thank you, Gai Liu.